Right. So we've been talking about aromaticity, and I just want to emphasize that you need to get good at being able to answer whether a ring that has heteroatoms in it is aromatic or not. You need to be able to deal with this situation. We talked about this a lot last time. This molecule happens to be called oxazole. Organic chemists like to impress people at parties by busting out impressive names of heterocycles like this. So I can point you towards a PDF document that shows you names of all of these things like oxazoladenone and benzotriazolyl something or other, and so you can use it at parties to impress other people. So let's talk about which pi electrons count. This is cyclic. Check, and it's fully conjugated. That is, you have sp2 or, you have atoms in the ring, each of which has a p orbital that can align with the other p orbitals in the molecule. But let's see if it has the right number of pi electrons. We're going to count the electrons in the conjugated pi bonds, 2 and 4. Now, last time we talked about these lone pair electrons. Do they count? No, they cannot count. They're not they wouldn't be in an atomic p orbital because we're already using that for this pi bond. They would have to be in an sp2 orbital that's held perpendicular to the pi system. It can't be involved at all. So you need to get good at recognizing that pattern. If the nitrogen's already involved in a pi bond, the lone pair can't be part of the pi system and does not count. How about on oxygen? Do both of them count or just one? Just one, for the same reason that you can put one of the lone pairs in a p orbital, but the other one would have to be in an sp2 orbital, again, perpendicular to the pi system, not participating. So you need to get good at knowing which ones count. 2, 4, 6, that's the allowed number of pi electrons. 6 electrons in the pi system. Yes, indeed, this is aromatic, which means it's got some special stability. In contrast, we could draw a molecule like this with 2 oxygens. Aromatic or anti-aromatic, how many pi electrons do we count? It's 2, 4, 6, 8, and the other 2 lone pairs we have to not count because they're not involved in the pi system. So this would be cyclic and fully conjugated because you have each of the atoms in the ring brings a p orbital with it that can align with the others. However, it has 8 electrons in the pi system and therefore is anti-aromatic. I will just point out that the allowed number, and this is a repeat from last time, of electrons in aromatic molecules is 2, 6, 10, 14, etc., defined by the series 4n plus 2, where n is just an integer greater than or equal to 0. Whereas anti-aromatic compounds have 8 multiples of 8, multiples of 4 rather, 4, 8, 12, 16, etc., following the pattern 4n. So the n, remember, doesn't mean anything. It's just an integer that defines the series. Molecules that are cyclic and fully conjugated and have 6 electrons are aromatic. Same with molecules that are fully conjugated cyclic but only have 2 electrons, and so on. Yes?
Does the 4n plus 2 rule apply for polycyclic systems?
Does the 4n plus 2 rule apply for polycyclic systems? Yes. Though you can get a bit confused as to which electrons count for which ring, and so you don't worry about it. Actually, you just count the total number of pi electrons: 2, 4, 6, 8, 10, 12, 14, 16. Huh? Did I miss something? Did I miss a pi bond? Maybe that would, okay, let's just not do that example since on the fly I'm struggling. Let's do naphthalene, which is just 2 benzene rings attached to each other. 2, 4, 6, 8, 10, that's aromatic. Yeah. Yeah?
What's the molecular geometry necessary for?
What's the molecular geometry necessary for aromaticity? That's good. Planarity is necessary for all of the p orbitals on these atoms that are conjugated to line up with each other. Now, your text lists planarity as sort of a criterion for aromaticity, and it is, but it's actually more of a consequence of aromaticity. That is, molecules that are aromatic will be planar. Molecules that cannot excuse me, molecules that cannot be planar cannot be aromatic, but I'm struggling to think of a molecule that would be otherwise aromatic that just loses on a technicality because it can't get planar. There probably is an example of that, but I don't know it. Yeah?
How do you know if the molecule is going to pucker or otherwise conform itself into a non-planar geometry?
How do you know if a molecule is going to...
Like you did like the octagon,
Uh-huh.
you animated top, and then I think if you
Right. So the question is, I've alluded to situations in which a molecule, because it's anti-aromatic, will actually distort itself from planarity in order to avoid that instability. How do you know when that's going to happen? Well, basically, what you need to worry about is the main criteria for aromaticity are cyclic, fully conjugated, and then the right number of pi electrons. And if you have that, the consequences are aromaticity, which comes with planarity. So I cannot think of a system right now where, oh, it would be aromatic because it satisfies all of these criteria, but it nevertheless can't be planar. I think you could probably build something like that, but I don't know what it is. Similarly, if you are not, if you are cyclic and fully conjugated, but have the wrong number of pi electrons, that is 4n, then the consequence is anti-aromaticity, and possibly not planar. The molecule might distort itself so as to not have to be anti-aromatic. That being said, you're probably wondering, okay, well, if something's anti-aromatic and distorts its geometry, should I say it's anti-aromatic or should I say it's just not aromatic? Say it's anti-aromatic. That's all that you need to do. Finally, what are aromatic compounds? What are compounds that are just plain old not aromatic? They are either not cyclic or not fully conjugated or both. Tons of molecules are not aromatic. Hexane is not aromatic. Cyclohexane is not aromatic. Cyclohexadiene is not aromatic, either because all of these are either not cyclic or not fully conjugated or both. Okay. Other questions? Yeah.
So really, when we're thinking about whether a compound is anti-aromatic, we're looking at the number of pi electrons.
That's right. If a molecule isn't, if we're looking at, if we want to determine whether a molecule is anti-aromatic, you're looking at the number of pi electrons. If a molecule is not cyclic or not fully conjugated, it cannot be. It can be neither aromatic or anti-aromatic. It's just not aromatic. Yeah.
How would you be able to predict if a lone pair is in a p orbital or if it's in like an sp2 or an sp3?
How do you predict whether a lone pair is in a p orbital or an sp2 or sp3 orbital? Okay. If a lone pair is adjacent to a pi bond, of an atom that is not already participating in a pi bond. Okay. If a lone pair is on an atom that's already participating in a pi bond, it cannot be in a p orbital. If a lone pair is on an atom that's adjacent to a pi bond, it will be in a p orbital, but only one can be in the p orbital. Only one of the lone pairs if there's more than one. Others? Yeah. Can there be R groups coming off the cyclic molecule? Yes. Yeah, so we'll talk about aromatic rings within larger molecules. For example, this box that we talked about has benzene rings all around the top. They are each individually aromatic. And I wouldn't ask, is this whole molecule aromatic or not? It's just like asking functional groups. Yeah. Okay, what else? Yeah. Nucleotide bases where you have a carbonyl group. So we'll come back to this when we do nucleic acids. For now, I'm going to draw, shoot, can I even draw a nucleobase from memory? I should be able to. I don't know which one I'm drawing here. It's either G or A. Don't tell anybody that I'm struggling with this, okay? I can do all the amino acids, but I struggle. Yeah, I think that basically looks good. This is aromatic, and there's experimental observations that you can tell that it is. For example, in DNA crystal structures, this is planar. Also, if you were to measure chemical shifts of, say, that proton, it would be in a region that's consistent with aromaticity. However, it's sometimes unclear which electrons you count, right? I would definitely count the 2 on this nitrogen. I would count this pi bond. I would not count those because they're on a nitrogen that's already in a pi bond. I would count, so let me just highlight this. I would count this and this, not those. How about these, and what about the ones in the carbonyl? And it turns out the way to rationalize that this is aromatic, and I think this is sort of an after-the-fact rationalization because the data tell you that it is. The way the Smith text explains that is to say, okay, well, if I can draw a resonance structure that is aromatic, then the molecule is aromatic. Right? So if I kick those electrons from this nitrogen down in the ring, suddenly I have 2, 4, 6, 8, 10, and that's an allowed number. And what this tells me is I would count the lone pair on the nitrogen, but not the electrons in the pi bond with the oxygen. We'll come back to that, and I'm not gonna give you something like this and ask you if it's aromatic. So I'm going to delete that. What else? You're like, not yet, I was still drawing it. Okay, I'll put it there for a while, but I'm telling you, don't worry about it. Okay, what else? Yeah?
If an atom is sp3 hybridized, does that rule out aromaticity?
If an atom is sp3 hybridized, does that rule out aromaticity? Absolutely. So these two atoms are sp3 hybridized, and sp3 hybridization rules out conjugation, and therefore aromaticity. Yeah. Okay. All right. So we can use aromaticity now as a potential explanation for why, for certain observations. So just real quickly, if I compare the acidity of this proton, I can't remember whether we did this last time or not, but if we did, versus this proton, we would need to draw the conjugate base, and then we can compare the two conjugate bases to see if there's a difference in their stability, and therefore if there should be a difference in the acidity of the orange versus the pink protons. Okay? So, what do you notice about these two conjugate bases? Go ahead.
The one on top is aromatic, and the one on the bottom is anti-aromatic.
Good. Aromatic on top, anti-aromatic on the bottom, and you concluded that based on?
The fact that the pi bond on the box, there's a lone pair. There's a lone pair on the bottom one that contributes, that can be delocalized across the ring.
Yes. So the lone pair on this atom is part of the conjugated system. Once you remove that proton, you satisfy the conjugated and the fully conjugated, and it was already cyclic to begin with. But that lone pair is part of the pi system now, and therefore you have 8 electrons, and that leads you to antiaromatic. On the top, you have the same conjugation and cyclic nature, but you have 6 pi electrons, and so you're therefore aromatic. So aromatic is special stability, antiaromatic is instability. So which of these protons is more acidic? Pink, right? And in fact, you would expect the pink proton to be more acidic than, say, a proton just adjacent to a pi bond. You talked probably in 351 about resonance and how the proton that's at this allyl position is more acidic than you would expect for an sp3 hybridized carbon-hydrogen bond. This pink one would be even more acidic still, because in addition to conjugation, you have aromaticity. In contrast, the orange proton would be less acidic than you would expect for being adjacent to a pi, or being adjacent to a pi bond. Finally, I'll just leave a problem for you to think about, and I want you to think about, and you'll use exactly the same kind of reasoning. Oh. I want you to sort of figure out which one reacts faster in an SN1 reaction, which is going to involve the chloro group leaving. And you'll rationalize that based on the stability of the carbocationic intermediate. So write that down. We're not going to do it now, but make sure you can answer that kind of question. Okay. What I want to do next is talk about where this rule comes from for 4n plus 2 electrons, and also why aromatic compounds are more stable than anti-aromatic compounds. To do this is going to require a little bit of molecular orbital theory. Understand that as I draw these orbitals, I'm never going to ask you to generate these from your mind. I'll tell you along the way what I expect you to be able to do. And if some of the MO reasoning isn't quite clear to you, that's okay, because in the end, you can just memorize the 4n plus 2 rule. But I find I'm unsatisfied by rules, because nature doesn't know anything about rules, right? Nature doesn't, it follows universal laws, but we can ask the question, why is the rule that way? And understanding that is important. So just a quick review. I want to start by considering a pi bond, and I'm going to draw the pi bond both from above and on its side. Conceptually, you should be familiar with the fact that a pi orbital looks like this. It has a lobe of electron density above the plane of the carbons and carbon-hydrogen bonds, because their geometry is trigonal planar, and then it has a lobe below. We get this pi orbital conceptually by combining 2 p orbitals together side by side in phase with each other. And so you may have seen or may have drawn a representation of a pi orbital sort of schematically like this, where you just draw the 2 individual p orbitals on adjacent atoms and they're side by side in phase. This looking sort of familiar so far? Ish, yes. Okay, understand this is not 2 different orbitals. This is how we represent a pi orbital most often. We could watch from above and we would see a lobe of electron density here, and below the ring we would see another lobe of electron density, with opposite wave function sign. The color here represents sign of the wave function. Understand that an electron is not hopping back and forth between these 2 lobes. This is a standing wave that the electron simultaneously occupies both sides. Its mathematical sign is say, positive here and negative here, and goes to 0 in the plane of this molecule. Now, one of the things you may not have had as much experience with is the idea that MO theory tells you that when you mix 2 atomic orbitals together, to make a bonding orbital, which we have called a pi bond or a pi orbital, you must also mix them together in the minus combination. And when you do that, you get an antibonding orbital, which we will call pi star. And the pi star we're going to draw just like this. And you can tell it's an antibonding orbital because the wave function goes to 0 in between the two nuclei, such that if I were to put electrons in this antibonding orbital, it would tend to pull the two nuclei apart. This place where the wave function sign changes in between the two nuclei is called a node. That's a term from wave, description of waves. That's just where the wave function goes through 0. So we'll draw the pi star this way, and it is an antibonding orbital. Now, for simplicity's sake, what I'm going to do for the rest of the molecules we talk about is I'm going to draw them from above, and a pi bond I'm going to represent as two circles on adjacent atoms. I will often not draw the lobes that are below the plane of the page. That is a pi orbital, and I will draw an antibonding pi orbital just by showing the switch of the wave function sign like this. Okay, so this is pi star. Pi orbital would be filled. The electrons in it would correspond to a pi bond. The pi star would be empty. Okay, am I telling you stuff you already know, sort of? It's okay, and it's okay if you're bored with stuff you already know, but people like to hear stuff they already know. It makes them feel smart. So don't ever, in a talk that you're giving about research or something, don't ever feel bad about telling people things they already know, because it makes them like you more, I think. Anyway, at least that's what, maybe that's my problem. Okay, so now we're going to talk about pi orbitals in a conjugated molecule. Have you seen the pi orbitals for butadiene before in the Diels-Alder reaction? Okay, I won't talk about them there, but the idea is you mix 4 adjacent p orbitals on each of these conjugated atoms together to get 4 new molecular orbitals. Now we want to do this both for benzene and for its linear counterpart, 1,3,5-hexatriene. And what I'm going to do is draw an energy diagram. And in 1,3,5-hexatriene, we have 6 p atomic orbitals on these adjacent carbons, and we're going to mix them together to get 6 pi molecular orbitals out. And in the case of 1,3,5-hexatriene, they are each different in energy. We're not going to worry about by how much. We're going to see that in between pi 3 and pi 4 is this boundary line between antibonding versus bonding orbitals. All right, so I want to draw just the 3 lowest energy orbitals, because they're the ones that are going to have electrons in it. In this molecule, I have 6 pi electrons. So in 1,3,5-hexatriene, I completely fill the pi bonding molecular orbitals and none of the antibonding orbitals. And pi 1 and pi 2, well, pi 1 at least is lower in energy than you would expect for just an isolated pi bond. And this is the energy you get. This is why conjugation is stabilizing, right? It allows 2 nuclei to spread out, 2 electrons to spread out over more atoms. And that moves them lower in energy. The lowest energy orbital, if we were going to draw it on on 1,3,5-hexatriene, the lowest energy orbital schematically would be represented by showing 6 atomic p orbitals on adjacent atoms. 1, 2, 3, 4, 5, and 6, all with the same wave function sign. Now, we're not going to take too much time to say what this really looks like is a delocalized orbital across the whole molecule with a lobe of electron density on the other side that's opposite in wave function sign. Okay, that's what we just drew here is this. And that lowest energy orbital in a conjugated system is always easy. It's just everything in with the same wave function sign. I'm not going to ask you to generate these pi orbitals from scratch or from your mind. Instead, I might show them to you and ask you to rank them in energy. And the way to do that is simply to count the number of times the wave function sign changes. So MO calculations reveal that the second pi orbital has a place right in the middle, in between atoms 3 and 4, where the wave function sign changes. That location where the wave function sign changes is called a node, and so we can actually rank orbitals by keeping track of the number of nodes they have. The lowest energy orbital has no nodes in between the nuclei. Pi 2 has one node. And then pi 3 actually will have two. And if you follow this pattern, actually drawing these becomes pretty easy. You just have to find ways to fit the nodes in that that work according to this pattern. There's also a symmetry requirement that I'm not even going to talk about. And I'm not going to ask you to generate these from scratch, but I do want you to see how the lowest energy orbital has 0 nodes, the second has 1, the next one has 2. You got that? A node is any place where the wave function sign changes. And yeah.
What's the variable value for wave function? I just don't know how to write it all out.
Okay, so what is, sorry.
There's like a letter.
Oh, psi. The Greek letter psi. I'm not sure if you pronounce the P or not. I guess you don't, because you don't say psychology. You could. Maybe that's what's wrong with me. Yeah. But you can actually use the term pi 1, pi 2, pi 3 to represent the wave function as well. Okay, so one other thing we need to talk about before moving on to benzene is you can get a sense for how low in energy a bonding orbital is by comparing the number of nodes, sure, but also by comparing the number of times wave functions are adjacent to, comparing the number of times the wave function has the same sign on adjacent atoms. When the wave function has the same sign on adjacent atoms, we'll call that a bonding interaction, because that's actually what a pi bond was. Same wave function sign on adjacent atoms is a pi bond. When that happens, that means the electrons in that pi bond can be delocalized in between the two atoms and pull them together. So what we would say, I'm going to note in blue the times where the wave function stays the same in sign between two atoms, and I'm going to call each of those times a bonding interaction. So there are 5 bonding interactions here. For pi 2, there are fewer. I have 4 bonding interactions, but I also have 1 antibonding interaction. An antibonding interaction is where the wave function changes sign between two atoms. We call it that because the pi antibonding orbital has this exact situation, and if electrons were in this orbital, they would not contribute to bonding between these two atoms. In order to determine the net number of bonding interactions, we simply subtract the number of antibonding ones from the bonding ones. So this would be overall net 3 bonding interactions, 4 minus 1 antibonding interaction. Can you sort of follow along what we're doing? In the next higher one, we have even fewer. There's 1, 2, 3 bonding interactions. There's 2 antibonding interactions. So we have just only 1 net bonding interaction. We could do the same thing for the higher energy orbitals, but that isn't going to be necessary. We're going to use this number of bonding interactions to compare the relative energies of these conjugated pi orbitals for the linear 1,3,5 hexatriene with what I'm now going to show you happens with benzene. But before we do benzene, any questions you want to ask about what we've done? I know I'm going through this fast. Go ahead.
For the second pi, yeah, is there 4 bonding interactions or 3?
There are 4, but then you subtract the antibonding interaction.
Okay.
Yeah, so this 3 comes from 4 minus 1, I guess.
Thank you.
Yeah, we'll put that here. Okay, others. Okay, so conceptually, we're going to make these same pi orbitals from benzene. Oh, wait, hold on, sorry. What would I expect you to be able to take from this? If I draw you pi molecular orbitals, you should be able to order them in energy simply by counting the nodes. Okay, so can you count? And maybe can you subtract? There's not even any division by 2. So this is very limited on the math. Now, conceptually, we will make these benzene orbitals by taking the pi orbitals from the linear 135 hexatriene and then pulling the orbitals on atoms 1 and 6 back around to be next to each other. What would that look like? Well, we could envision if we make pi 1 cyclic, that's going to look like this. And nothing will have changed, only we've pulled atoms 1 and 6 back around to be close to each other. Now, what does this do? What is the difference? See if you can spot the difference between this linear orbital and this cyclic one, because I'm going to tell you this cyclic one is lower in energy than the linear one. So why? Yeah.
Because there's an extra bonding interaction, how they pull the 6 and the 1 next to each other.
Bingo. Ding, 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 ding. Excellent. We have, because we've made it cyclic, these are the 5 bonding interactions we had previously, and this is the new one. The new bonding interaction that we get when you make them side by side. Okay? So when we tell you that aromaticity is a special stability, what that comes from is combining conjugation with cyclicness, because you get a bonus interaction. So that's one way that aromatic molecules are more stable than their linear conjugated precursors. This pi 1 for benzene is going to be lower in energy than pi 1 for the linear combination. Now, let's do the same for pi 2. And let's just try to illustrate what happens there. Let's bring that around. Let's see, 1, 2, 3, 4, 5, 6. I'm going to try to keep everything the same as it was above. 1, 2, 3, 4, 5, 6. There is one node there, just as there was one node previously. Interestingly, this orbital has the same number of bonding interactions, but it has one additional antibonding interaction. So pi 2 is actually probably, pi 2 in benzene is probably a little higher in energy than pi 2 for 135 hexatriene. Now you might be saying there, well, hold on, you told me benzene was more stable, and it is, because pi 1 moves down in energy. It's true that pi 2 moves up in energy, but we're going to see in just a second that pi 3 actually moves down in energy to match the level of pi 2. Okay? Questions about getting here? You don't have to worry about getting there, actually. I mean, I would show you these orbitals and you could rank them in energy, but I want you to understand sort of where the special stability is coming from. Pi 3 is trickier to see. And so I'm not going to attempt to make it from this linear precursor. You're just going to have to accept that what I'm about to draw comes out of the math, or maths, depending on what you like to say. So pi 3 looks like this, and you have a node that corresponds to the middle atoms there. Just for the sake of being able to discuss, we're going to say that the node passes through atoms 3 and 6. So pi 3 has one node, just like pi 2 does. And if you count up the number of bonding interactions, pi 3 has 2 bonding interactions, just like pi 2 does. The reason we don't count this switch in wave function sign as a anti-bonding interaction is because it doesn't happen in between two nuclei. The node actually coincides with those atoms. You never have a situation where the wave function is on adjacent atoms but opposite in sign. So if these orbitals, pi 3 and pi 2, have the same number of nodes and the same number of bonding interactions, they must be equal in energy. They are different in shape, but equal in energy. And there's a mathematical term for that. It's called degenerate. It doesn't refer to their moral qualities, but rather to the fact that they're equal in energy. How does this change the orbital diagram for 1, 3, 5, relative to the linear precursor? Okay. So it will turn out, and we're actually going to not even worry about these antibonding ones. We said that having the extra bonding interaction brings pi 1 down in energy. We said that having for pi 2, we have one fewer bonding interaction. But for pi 3, we end up having, if you compare to what we had previously, pi 3 before only had one bonding interaction. Now it has 2. So that cancels out the problem of moving pi 1 up in energy because pi 2 moves down in energy by a corresponding amount. No change there. The big change is then that pi 1 is lower in energy. And it will turn out that if you calculate the energies of the antibonding orbitals, you also have a pair of degenerate antibonding orbitals and then one highest in energy. And if you want to see what pi 4, pi 5, and pi 6 look like, the Smith text will tell you that. You can take a look. This is where the 4n plus 2 rule comes from. The 2 reflects the fact that in an aromatic molecule, you have 2 electrons in this lowest energy stabilized orbital, and then thereafter you have pairs of degenerate orbitals that can each accommodate 2 electrons, so you have 4 electrons total from 2 degenerate pi orbitals. Why the 4n? Why not just 4 plus 2? Well, it will turn out that if you do a similar energy diagram, imagine a 10-membered ring. I'm asking you to imagine it because I can't draw it. But if you did the math for the 10-membered ring, what you would discover is you have 5 bonding orbitals, 1 lowest in energy, then 2 sets of degenerate higher energy orbitals, and then 5 antibonding orbitals in the same way. If you had 10 pi electrons, that will allow you to fill 2, and then multiples of 4 allows you to fill up all of the bonding orbitals without filling any of the antibonding orbitals and not having any unpaired electrons. So n refers to the fact that depending on how big my ring is or how big the aromatic molecule is, I'm going to have pairs of degenerate orbitals that can each accommodate 2, so 4 electrons at each of these levels. 2 is the lowest one, and then the 4n is for each pair after that. That's where the rule comes from. Now, we've done questions you want to ask so far? Getting there? Yeah.
Just back up to the pi 2 and pi 3 bonding orbitals.
Yeah.
I was curious why you had 2 antibonding, like there's one node, but you had -2.
Uh-huh.
The other one you had what seems like the equivalent.
Right. The reason we have -2 here for pi 2 is because we have a wave function change in sign in between 2 nuclei. In contrast here, the wave function doesn't change sign, it just goes to 0. And similarly here, it doesn't change sign, it just goes to 0. So we're not counting that as an anti-bonding interaction because the wave function switch doesn't happen in between two nuclei. Yeah. And to some extent, this is just hand waving because what I'm trying to do is create a qualitative story that gives you the answers that the math tells you. Yeah. It involves matrix math. Do you want to do that? Determinants? No. Okay. Neither do I. I wrote a Mathematica file once that did it for me, though, so that was kind of fun. Fortunately, there's a mnemonic device that, if you are careful with drawing circles and polygons, gives you pretty well quantitative descriptions of the energy levels of these molecules. For example, for benzene, if you draw a circle, I just discovered this feature. I can draw a nice circle now. And then let's see if we can do a hexagon. All right. Inscribe the hexagon in a circle, and every time a vertex hits the circle, that's where an energy level is. And if you measure these distances, they turn out to be proportional to the calculated energy differences between those orbitals, which is kind of cool. I don't know why it works, but if you forget this pattern, all you have to do is draw the single ring, point down in a circle, draw the lines every time the six-membered ring hits the circle. That's where an orbital would be. The midpoint of the circle is the boundary between antibonding and bonding orbitals. And then you take the number of pi electrons that are available to you, and then you fill the orbitals. And you'll see that with benzene, we fill the lowest energy one and then the two degenerate higher energy orbitals. Yes?
Can you show us what that looks like with a 10-membered ring?
Can I show you what? Sorry?
What that looks like with a 10-membered ring?
Can I show? Hardy har har har. What does that look like with a 10-membered ring? Yes. But first, I will show you what it looks like for a 4-membered ring to explain why cyclobutadiene is unstable. So, and we may need to say something about this next time, but if you draw the 4-membered ring and inscribe it there, and then put a line every place where the ring hits the circle, and then fill it up with the available pi electrons, according to Hund's rule, what you get is this. Now notice, problem number one is you have unpaired electrons. So you expect cyclobutadiene to react as a diradical. Problem number two is that this degenerate pair of orbitals occurs in an area that's neither bonding nor antibonding. It's non-bonding. So in cyclobutadiene, you thought you had two pi bonds. Wrong. You have one, and then you have two unpaired electrons that are not stabilized by bonding at all. So this is why it's worse to be antiaromatic than to simply be not aromatic. And what this molecule will try to do is change its geometry that will break the degeneracy between these orbitals and lower one of them. Oh, well, I have to show that to you another time. It will lower one of them here, and then that electron can go there, and it won't be unstable anymore. All right, that was too much. While you're leaving, I'm going to try your 10-membered ring and see if I can get it.